All right, so here's how I still have to figure out the timing. We've got about 3 days to get through projectile motion, which will be today, tomorrow, Monday. And we don't have class Friday because we're having our parade like a week from this Friday.
Wow.
So your midterm final will either be Wednesday or Thursday, depending upon how projectile motion goes, okay? And how involved we get with that. I'm leaning more towards Thursday. Earliest would be Wednesday. And that's going to be kind of comprehensive from day one. But it kind of has to be, because if you look at force equals mass times acceleration, well, if you can't do acceleration, you can't do forces, and so it kind of lends itself towards that. So the only thing kind of new under the sun is this concept of projectile motion. Now, projectile motion, it's a new topic, but it's basically the same idea, but we're just going to repackage some ideas, okay? So with projectile motion, here's what's going to be different. All the motion that we've ever talked about so far has either been one direction or the other. So like you've had a car driving along and it stops, or you shoot a cannonball up in the air, okay? And so all of our x calculations involving friction, acceleration have always been in the x. And all of our calculations in the vertical have been involving gravity, the gravity mafia, whatever that may be. So what changes is that with projectile motion, now we're going to combine the two together, okay? So as I say that, but here's also going to be your overriding theme with projectile motion. Is that what happens in the x stays in the x, what happens in the y stays in the y. Now, we combine the two together to get like a resultant velocity, but that's going to be your overriding theme. What happens in the x stays in the x, what happens in the y stays in the y. So there's basically going to be two categories of these projectile motions. What I call ground to ground, so that would be like you hit a golf ball and it has some motion like this, okay? So you're going to have a horizontal component of that velocity and you're going to have a vertical component of that velocity, okay? So the biggest difference is going to be with a ground-to-ground problem, you start with some initial vertical velocity, okay? Louis?
I wanted you to throw it.
Like that?
Yeah.
Good. So as that ball is traveling to Louis, right, it has some vertical velocity component to it, and it has a horizontal component to it. Now, and this is going to be true on both of these. Here's the main assumption that we're going to make. And this is going to be true of both of these. We're going to assume that your horizontal velocity is constant, okay? So we're going to assume that there's no external forces acting in the horizontal direction, okay? Just like, when we did the Limb Lab, and we talked about, hey, if you're on the moon or if you're on the Earth, and, the horizontal calculations are the same if you neglect air resistance. So that's what's going to happen here. Now, in reality, especially those of you that have played, especially soccer in the state of Kansas, you know that if there's a strong wind, that horizontal component of that velocity changes drastically. Versus like if you're trying to kick it into a strong south wind, there's really no point, okay? Versus if you hit it with a strong south wind, that ball is going to carry forever. But that's going to make things horribly complicated. Because then you have to get into drag coefficients and, well, what is the horizontal acceleration? Well, is it big? Is it small? Is it a smooth surface? Is it a rough surface? Are you going into the wind? Are you going with the wind? What's the relative humidity? All of those things in reality play into a horizontal acceleration. And physicists are famous for this, like, that's annoying. Oh, let's just ignore it. Again, that's what we do. We just ignore it. And the same thing is true when we drop something. We assume that everything falls in a vacuum and the acceleration is 9.8 meters per second squared. In reality, it's not. It's actually less than that, okay? But that, again, that just makes it complicated. So it's like, screw it. Let's just use 9.8. So because my horizontal velocity is going to remain constant, one of the equations that we're going to use, and this is going to look fancy, r equals Vx time, and r is your range. So your range is your horizontal distance. So here, Louis, give that throw back, okay? So when Louis throws that ball to me, the range would be the difference between Louis and me, okay? So range is just your horizontal distance. If I throw it to Beckham, then that's going to be a much greater horizontal distance. But what we're going to assume that because that horizontal velocity is constant, all we're using basically is distance equals velocity times time. So what that means is, like on a velocity time graph, we're assuming that whatever velocity you have horizontally to start with, that's going to remain the same. So we're going to assume that there is no horizontal acceleration, because that's just going to make the math easy. So, whoa.
Got a little arm behind you.
Oh, say, wow, a lot of EX, man. Whoa, smoking. Okay, so this is why I say what happens in the X stays in the X. So with lemming problems, and does anybody know what lemmings are famous for? Okay, so according to the legend, this is in England, that there's a cliff, and these lemmings, which look like basically rats or gophers, that they all come running to the edge of the cliff, and they jump off the cliff, and they jump into the water and meet their untimely end, okay? So this is what lemmings are famous for, is jumping off the edge of a cliff, okay? So if someone says, don't be a lemming, okay, what they're saying or implying is that don't be like everybody else and jump off the cliff just because that's what everybody else is doing, okay? So here's what's going to be the difference. With a lemming, the only velocity that you have to start with is Vx, okay? So in other words, instead of throwing the ball to Louis like this, I'm going to throw it to Louis, but I'm going to throw it completely horizontally, okay? Ready? So with this one, right, I threw it completely horizontally without any initial vertical component to it. So with the lemming problem, let me kind of draw this. So
Bouncy.
you're going to get a path like this. So let's say your Vx is, 5 meters per second. And your Vy initial is going to be 0. So if something just jumps off of a cliff, the only velocity that you have is the horizontal. And as it falls through the air, we're going to assume that Vx is going to stay the same, and there will be no change in that horizontal velocity. Okay, that's going to be huge. Your Vx is not going to change. So let's say that I am about 2 meters above the ground, okay, and pretend that we haven't studied anything about projectile motion. You don't know anything about forces. You don't know anything except that you're getting ready for the acceleration test, okay? So none of this exists. I'm going to tell you, here's the apple. I'm going to drop it, and I'm going to let it fall 2 meters, about like yay, okay? I want to know how long it's going to take for that ball to hit the ground. So what information do I have to give you?
Time.
No, I want you to find time.
Acceleration.
So what's your acceleration going to be?
Negative 9.8.
Initial
Negative 9.80 meters per second squared. I dropped it,
V naught,
so V naught is going to equal
0 meters per second.
0. And I want to find
We need the distance.
time. And it's going to fall 2 meters.
Okay.
So what am I going to use to find that time? You're getting ready for the acceleration
Square
test.
root of 2x over 8.
2x over 8. And that comes from x equaling 1/2 at squared plus v naught time. Okay? It's an equation that you all know. V naught is going to equal to drop out. You solve for time. You take the square root. Boom, there you go. Okay? Everybody good with that? And now you're thinking, oh, that would be so simple. Whew. Wow. Okay? So let's do the math. So somebody take 2 times technically negative 2 meters, and technically divided by a negative 9.8 meters per second squared. What do you get?
0.3.
It's going to be less than 1.
0.4,
0 point. No. Did you take the square root of it?
Be about 0.2.
Man.
It should be 0.638.
638
That makes sense.
seconds.
Yeah.
Now, here's what you're going to see as we get more and more into complex equations. Not only do you have to look at what is in the equation, which is important, you also have to look at what is not in the equation. Okay? Because that can tell you just as much information. So, did I have to tell you that it was a green apple?
It would have helped.
It would have helped.
Yeah,
Okay.
those are the good ones.
If I had used a red apple, would that have changed that answer?
No,
Why not?
because it's still the same mass, follows the same distance, same acceleration. Yes.
Here's the point. Is there any way, you're right, but I want you to see something else, Louis. Is there any way to plug in the color of that apple into that equation?
No.
No. What's the only two things that you have to calculate that time?
Distance and acceleration.
You have to have distance and you have to have
Acceleration.
acceleration. Did I have to give you the mass of the apple?
No.
No,
Why not?
because you have the equation.
It's not there. Okay, you can't plug the mass of that apple into that equation if you tried. It's not there. I didn't give you the mass of the apple. Didn't tell you that it was green. Didn't tell you that it weighed 1 newton. Didn't matter. You know why? That's not part of the equation. So if I take this apple, or if I take Hank the bowling ball. So I've got the apple, I've got Hank, right? I drop them. Which one's going to take longer to hit the ground? The apple or the Hank, or will it be the same time?
Same time.
Same time. Why?
Because it's the same acceleration.
Same acceleration, same distance, right? They would both hit the ground at the exact same time.
Let's test it.
No.
Yeah, lay on the bed of
No,
nails.
because I just got, yeah, that's it. I'll lay on the bed of nails. That would be the ultimate trick. I'm going to lay on the bed of nails with a Hank falling from the ceiling and crushing the concrete block. What could possibly go wrong? Nothing.
Hey,
Solid. Okay? Physics teacher impaled by Hank the bowling ball. Okay. Yeah, ironically, I trust Louis with the sledgehammer before I trust Hank falling from the ceiling. Okay.
became an extra stone.
It's funny, one of my students yesterday sent me a video, and it was the teacher that was doing the swinging of the hammer.
Wait, you put the kid on the bed of nails?
Well, it was worse. So he didn't have the full bed of nails, he just had like a section of a bed of nails, and the block was on top of that. And the teacher was coming down with the sledgehammer, and the kid flinched and moved it, and then he actually hit the kid with the sledgehammer.
Oh my gosh.
Yeah.
That kid has the fattest lawsuit coming.
Oh, yeah.
Oh,
Just-
that's great.
Oh, it's just like, so he sent that to me. And then I responded, and I sent him back the video of you hitting me, and I said, this is how it's done.
Okay, can I see that? Because when I watched the lesson, someone didn't record it on the camera on YouTube, so I didn't get to see it. I just heard it happening in the background.
I'll show it to you.
Okay, thank you.
Okay. I've actually got it in slow motion.
He was recording with his own phone.
So, okay. So,
Oh yeah, I did.
now,
Selling.
what
That's
if
my bad.
I ask you to calculate the velocity of the ball at impact, and we can't use the time?
That equation.
We use that equation. V squared equals V naught squared plus
280.
2AX. V naught's going to drop out, go to 0, right? So somebody take 2 times technically negative 2 meters times negative 9.8 meters per second squared.
God knows.
It's 6 something.
39.
6.26.
6.26 meters per second. Now again, I drop Hank. I drop the apple. Which one's going to land with a greater velocity?
Nothing.
No, neither.
It's going to be the same, right? Mass is not a factor. Everybody cool with this?
Yes.
Got it. Good?
Yes.
Brain. Okay. Now, I'm going to launch the marble horizontally 2 meters above the ground. Okay? So I'll visualize this, and I'll show you this demo in just a second. I'm going to launch the ball straight out horizontally. At the same time, I'm going to drop a ball. Okay? One's going to shot out horizontally. Not up, not down, horizontally. The exact same time, another ball is going to fall straight down. Which one will hit the ground first?
Same time.
Yeah.
At the same time,
Why?
because mass or I guess like direction is not a factor. It takes the same amount of time for both to fall
Why?
because
You're right.
because gravitational acceleration is the same.
Okay.
What stays in the Y?
What'd you say?
What? What happens in the Y stays in the Y.
And what happens in the X?
Stays in the X.
Stays in the X. As long as I shoot it out horizontally, is there any way at all to plug Vx into your time calculation? No. So, Vitor, I want to go to the kind of in the middle of the room so you're going to have to give that a spin.
Oh
So, what I have here
my. Casey Neistat, who?
is a contraption just for segmentation. So, this has a spring I can pull back, and we'll talk more about energy later. I'm storing potential energy. Mother Nature doesn't like potential energy because so as soon as I flip it, she changes potential energy back into kinetic energy. So I'm going to pull back on this. I'm going to lock this in place, and this is a specially designed ball just for this. Has a hole through it. So I'm going to hook that on the end so that when I do this, that just falls straight down. Okay? So I'm going to have it here on the corner. So I'm going to pull this back. I'm going to hook this one here. And then this one's going to get launched out. Okay? So when I flip this one's going to go out, that one's going to fall down. So here we go. Now, as predicted, what happened? It hit at the same time, right? So if I were to do that calculation of time and how long that's going to take, that one is going to take the exact same time as that one that gets launched out. Okay? Mainly because if you look at what's a variable, as long as they're shot out horizontally or dropped, there's only two things that make a difference, and two things only. How far they fall, and what that gravitational acceleration is. Okay? There's nothing else that matters. Not the mass, not the fact that this one has a hole, drilled through the middle and I can see Louis. Okay? It's not part of the story. Okay? Not part of the story. Got that idea?
Yes.
Okay. Now, Vitor, give that a spin back.
Spin back.
They're about to spin.
Spin back on
Spin back on the opposite.
Vitor's big back.
As long as I have an A.
Go Clemson.
Tigers.
Over the 80 figure.
We got the same
Give me 1 second. I gotta start this saving process
Sorry.
because I gotta do like
So
all
it comes
the
down
It's
to
just so
time.
empty.
It comes down to time taken then. Lou was done first.
Yeah, no, you should have been. You should have been docked at least 5 points for taking
Why?
like 2.5 hours. On
There's no time limit.
That's crazy.
There's no time limit.
Yeah, there was a time limit to get on the bus. You almost went away.
You got on the bus?
I almost missed the bus. I almost missed the bus.
Oh, yeah.
When did the bus leave?
We got there like 2 minutes
I had to go home.
We get out 2.5 hours.
I would rather get a 95 than.
Imagine if we had this first one. You would be so.
Yeah.
That would suck. But you can come in before then.
That's true.
But how would he know it's gonna take him that long to take that down?
I would have missed a whole nother class, bro.
You
I would've
missed
missed
a
all
class and a
second.
half.
No, because there's only, it doesn't even an hour extra. You got out 2:35.
You said you got to
3:30.
3:30.
Yeah. But we usually get out at 2:35. So it's 55 minutes long.
Is that still recording?
Yeah.
Why? Do you see the red light?
What do you want me to do? Pause it?
What's today's date? 6?
Yes.
Yeah.
He's not.
All right, now, so now I want to change up the problem. Instead of dropping it from 2 meters, now I want to drop it from twice as high, and we're going to drop it from a height of 4 meters. Okay?
2 times 3.
So I want to find the new time, and I want to find the new velocity. Since it's going to fall twice as far, is the time going to be twice as much?
No.
No.
Yes.
No.
No.
Acceleration is exponential.
No, it'll be
No.
twice.
Acceleration is 9.8 meters per second squared.
It's exponential.
To find the time, you take a square
Time
root,
is
so
twice
it's
as
not gonna be
much,
twice
so
as much.
distance.
No. Distance is going to be twice as much.
Yes.
The question is will time double?
No,
No.
it's a square root.
Okay, so let's settle the argument.
Yeah.
Okay?
Alright.
So one option is that we're going to do smash mouth physics.
No way. we
Okay.
say-
So somebody take 2 times 4 meters and divide that by 9.8 meters per second squared.
Yeah, because a distance time graph is exponential.
0.9.
0.9.
Exactly?
Yeah.
Okay?
It's not too tough.
So if it had doubled, the initial time was 0.638 seconds. So if it had doubled, that'd be about 1.2 seconds, right?
Yeah.
So it didn't double.
No.
Now, but that's a smash mouth way of figuring it out. The more elegant approach is to do this. This is how you calculate the time, right? 2y over g. I'm going to use y because I'm talking about a vertical distance. I'm going to talk about g because I'm talking about the acceleration due to gravity.
Yes.
So this was the initial way to calculate this, right? Now, if I double the distance, and I'm going to use t prime. T prime means like this is going to be the new time. So when you see prime, we're going to use that a lot when you get into momentum, especially in energy. So prime just means this is going to be something new. So how can I rewrite this doubling the height?
For what?
Well, I can write it as 2 times 2y over g. True?
Yeah.
Same thing. Okay, which is 4, but there's a reason I want to write it like this. There's a method to the madness. Now, can I rewrite this as the square root of 2 times 2y over g?
Yes.
Is that cool?
Yes.
Right?
Yeah.
Everybody cool with that? Now, out of curiosity, so this method shows that it's going to increase by the square root of 2. So somebody take the square root of 2 and multiply that by 0.638. How cool is that? You got the exact same answer. Okay? Whoa, trying to catch you, okay? So, I don't care how you think this through. You can do smash mouth physics. You can take the more elegant approach. I don't care. Now, what's going to happen to my velocity if I drop it from twice as high? Will my velocity double?
Without using time.
Doesn't matter.
Yeah.
B squared minus B naught squared over time.
What?
Wait, no.
What? He's using this
B
equation.
equals this equation?
That's the equation that we used, right? To find the vertical velocity when it
Yeah.
lands. True?
Yeah.
Initial velocity is,
Well, not double
so I've got the square root of 2a.
x. Well,
So
not.
it's going to do the same thing.
It's not gonna double.
So if that's my
Oh,
initial
mine.
velocity, my v prime is gonna be 2 times
A times
2a, or 2x,
Yeah, 2x. Times A.
times a, right?
Yeah.
So what's gonna happen?
It's gonna increase by the square root of 2.
Yeah, that's also gonna increase by the square root of 2. Because if I pull that out, I get that. Now, the other way that you can think about it, and that's kind of something what Louis kind of alluded to, if you look at v equals v naught plus at, so my velocity changes as a linear function of time. So if I'm in the air the square root of 2 times longer, my velocity has to increase by the square root of 2 as well. So you can think about it in terms of this equation or that equation, okay? Now, what's going to happen to the time if I double the mass?
Nothing.
Absolutely nothing. Why?
Can't plug it
It's not
in.
in there.
It's not part of the
variable.
equation, okay? Now, here's how this all fits together. So I'm going to launch this ball horizontally, and let's say that that Vx is, I don't know, 10 meters per second. Okay, pretty good clip. Like, most people can't even run that fast. So we're going to launch this ball out at 10 meters per second at 2 meters above the ground. So I want to find out a couple of things. I want to figure out how long it's going to be in the air. I want to know the Vx when it lands. Okay. I want to know the Vy when it lands. I want to know the overall velocity, which is a resultant of those two, Vx and Vy. And I want to know how far it's going to go. Okay? So, I'm 2 meters above the ground, about like yay. I'm going to throw this thing at 10 meters per second. Okay? So, I want to know at the point of impact when it lands, I want to know all of those things. Now, we've already done the time calculation, right?
Yeah.
Okay, we've been down that road. So that was the square root of 2 times 2 meters divided by g. What was that, 0.62, 0.638? What was that time? 0.638
Yeah.
seconds. Okay, so we already have that number. So that's 0.638 seconds. Now, when it lands, what's my horizontal velocity going to be? Do not make this difficult.
10 meters per
10
second.
meters.
10 meters per second. Because what we're assuming is that horizontally, there's no external forces. Without an external force, there's no acceleration. Without an acceleration, your horizontal velocity remains constant. So that's still going to be just 10 meters per second. Now, when it lands, okay, when it lands, is the vertical velocity when it lands and it falls straight down the same vertical velocity it has if I throw it horizontally?
Yes.
Yes.
Yes, because again, is there any way to plug Vx into that vertical velocity calculation?
No.
No, because what happens in the
X
stays in the X, and what
X.
happens in the
Y
stays in the Y. Okay? So that vertical velocity is going to be the exact same, which is still going to be, what do we get, 6.26? Oh, come on. Seriously? There we go. 6.26 meters per second. So visualize this. Here's the ground. Here's this ball coming in. So the horizontal component of that velocity is 10 meters per second. I gave you that number. Okay, we have that number. It's also going to land with a vertical velocity of 6.26 meters per second. Okay? So if you think about this in terms of like a resultant vector, so what I want to find is the speed. So in projectile motion problems, when you hear the word speed, okay, what you're talking about is like how fast this thing is going. So one way that if you can visualize this, imagine that you had like a radar gun in the ground. and that radar, and you're shooting that radar gun at that object right as it lands. And what you're trying to figure out is what's going to be the speed as measured by that radar gun at that point of impact. Now, your radar gun can't differentiate Vx and Vy. Your radar gun is just saying, hey, this is how fast this thing is going. Okay, that's the only game in town. So what you can do is, this is why we have to deal with vectors. So you got a Vx at 10 meters per second. You've got a Vy at 6.26 meters per second. So that resultant is going to be the speed. So that's going to be the net effect of those two velocity vectors acting at the same time. So, Devin, how can I find that resultant?
Pythagorean theorem.
Fantastic. So somebody takes 6.26 squared plus 100,
11.8.
11.8.
Lou's on it, bro.
Louis, Rod is calculating a game, right?
Okay.
So what that means is if you were in the ground with a little radar gun, as that apple, just at that point of impact, if you could measure that speed, it would be going 11.8 meters per second. Okay, so that's the actual speed of the ball.
That's when it hits the ground? Or?
Yes.
Okay.
Just at that point, just right at that point of impact.
Okay.
Okay? Got that?
Yeah.
Okay. Now, could we find that angle
Yes.
using what?
Sine.
Tangent.
I'd go tangent. Mainly because sine's going to involve that hypotenuse
Right.
calculation, and if I screwed up the hypotenuse, I'm going to screw that up. So I do a little inverse tangent action, because let's say I want this angle right here, which in the lab, that's the angle that y'all are going to want, is that angle right there. So a little inverse tangent of 6.26 over 10. Now, before you touch the calculator, is that angle going to be bigger or smaller than 45 degrees?
Smaller. No, bigger. No, smaller. Smaller. Smaller.
Smaller?
Yeah.
Why?
Because they're not the same.
That's true.
And the opposite side is smaller than the...
Yeah, and your y component is smaller than your x component. Now, so somebody do that angle. Take the inverse tangent of 6.26 over 10. And make sure you're not in radian mode, Louis. What'd you get? 32.0 degrees. So that would be that angle in there. Got it? Good? Great.
Laptop.
Okay, so stop that. All right, so the lab itself, in terms of technical difficulty, is not going to be that big a deal. So what you're going to do is,
I fixed it.
Vitor, give that, make sure they can kind of see this setup. So what you're going to do is you're going to take a ramp, you're going to hold up a marble, and then, oddly enough, you're going to let that marble roll down. So speaking of energy, when you're holding that up, that's potential energy. Mother Nature doesn't like potential energy. Mother Nature likes
Kinetic.
kinetic energy. So as soon as you let go, what's the ball going to do?
Accelerate.
It's going to accelerate. It's going to change that potential energy into
Kinetic.
kinetic energy. So you're actually going to do this back there on the tables up there, but I've got to do it up here, so it's a little bit shorter. So you're going to hold it up like this, and then you're going to let go of it, and oddly enough, it's going to turn into a projectile. So, really? That's, no.
Just tongued his marble.
So,
I didn't actually.
I know. But it's just the thought that you might. Oh, okay. I'm
Louis'
gonna go
idea.
on iron
You
today.
did.
I think I'm gonna swallow
I'm hungry.
a ball bearing. Okay, kind of weird, but if that was.
The intrusive thought.
So here's what you're gonna do. Here's gonna be your ramp. You're gonna clamp that onto the table. Ball's gonna go flying off, and it's gonna turn into a projectile. Make sure that the ramp is horizontal. That way it's a lemming problem, okay? Don't tilt it up, don't tilt it down, make sure it's going off like this. So, you're going to measure the height, and you're gonna use that to calculate the time, okay? Now, you're gonna measure the range. To get the range, we're gonna kind of take advantage of carbon paper. So carbon paper is a
Looks like
wonderful
sushi
thing.
paper.
So what happens with carbon paper is that what you're gonna do is get an idea of where it's gonna land, and then you put a piece of paper down where you think it's gonna land. Then you take this piece of carbon paper, diamond side out, okay, and lay that where you think the marble was going to land. Roll the marble down, and when it hits, okay, like this, what's gonna happen is that's gonna transfer some of that carbon paper onto this paper. That way you're gonna have an exact measurement of where it lands. So then you're gonna measure from the base of the ramp where it turned into a projectile. You're gonna have to transpose that mark down onto the ground, and then you're gonna measure that range. So it used to be, back in the Dark Ages, shortly after the dinosaurs went extinct, that when you type something, and this is where CC on an email comes from, carbon copy, that's what carbon copy stands for, okay? So it used to be, before laser printers and everything else, or emails, if I were to type, let's say I needed to write a letter of recommendation for Louis, okay? So say, to whom it may concern. So I'd have my original piece of paper that I'm gonna put into the typewriter. So you'd have to sit there, roll it, boom, paper goes in. It's plain, okay? And what would happen is that I would write to whom. So I would write to whom. And so what happened is that this was a mechanical process. So the letter, a ball or a lever or something, would come up and strike the letter, and it would transfer ink onto this. So if I wanted a copy of this, and this is back before copiers even really existed. So if I wanted a copy of this for myself, what I would do is I would take my front piece of paper, so I'm going to send the original to Louis' scholarship committee. So then I put a piece of carbon paper here, and then I put another piece of paper here, back behind it. So then when that letter came up and physically struck the front page, then it would because there's carbon paper behind it, it would transfer that image to the second one. And so that's why when you do email, when it says CC, that stands for carbon copy. Because that's a throwback to the old days where, and down at the bottom, I would say, so I would send a copy to Louise, okay, and then at the bottom I would say CC, Stan Burkamp. That way that the people that got it knew that I kept a carbon copy of that. Or maybe I would do two of these, and I would make sure Louis got a copy of it. So then I'd put CC, Stan Burkamp, Louis, so that the people know that they would be aware of who else had a copy of that letter. So now they have BCC, which is blind carbon copy, so that means I could send a letter to the university, but then, I'm going to send a letter to Louis. I don't want them to know it, so that's why I do the BCC. So that's where the old school CC comes from. So the only data that you're going to collect up here is going to be the height of the table and the range. Okay, that's it, nothing else. Don't ask me for a stopwatch, okay? You're going to calculate the time. So it's going to be a calculated time. You're not going to measure it, you're going to calculate the time. Make sure that you're showing all of these calculations because everybody's data is going to be different. Show me your calculations, okay? Now, you're going to calculate your Vx. You're going to calculate the final velocity. So what's going to happen is that this is what I'm going to want. You're going to know your Vx and you're going to know your Vy. So where I say V resultant, that's what I want as the hypotenuse of that triangle. And then the angle is the one that I want right here. And don't worry about getting weird and subtracting that from like 360 and making it like 350 degrees or something like that. Don't make this complicated. Just give me that angle right in there. That's typically around 75 degrees-ish, okay? If you get like 90, you did something wrong, like it fell straight down. Cool, okay? So then you got a bunch of questions to answer. Read what's happening with these graphs. One is a horizontal velocity time graph. So here's the situation. On question 6 and 7, imagine this. One, I drop it straight down, and the other one rolls off the end of the ramp. Okay? So at the same time, just like I did back there, one's going to get dropped, one's going to roll off the end of the ramp. You're going to draw a horizontal velocity time graph and a vertical velocity versus time graph. Make sure I know which line is which. Which one is the one that is dropped and which one is the one that is rolled off the end of the ramp. On the back side, these are all questions that you need to answer. When you get down about a third of the way down, what I did is I took a car, you drove it off the cliff at 112 kilometers per hour, 15.8 meters high. You're going to do a whole bunch of calculations of time, range, Vx, Vy, and the velocity of the impact. Then I'm going to change it. Instead of going 112 kilometers per hour, the guy was driving twice as fast and was going 224 kilometers per hour. So what you want to do is tell me what's going to happen to time, what's going to happen to range, what's going to happen to your vertical velocity. Do not just tell me, oh, it's going to increase or decrease. You can do this one of two ways. You can either actually calculate it, so it's like, I'm just going to do smash mouth physics, okay? And you actually go back and do the calculations. And you tell me, oh, this is going to be the time, and you actually calculate it. If you want to go with a more elegant approach and go, oh, it's going to double, or it's going to increase by the square root of 3, or it's going to increase by the square root of pi squared. I don't care, okay? I don't care how you do it. If it's not going to change, just say, hey, it's not going to change. But if it changes, just don't say it increases or decreases. So you can either tell me, you can either calculate the value or tell me exactly by how much it changes. Pop.
So for the range there, is that the
How far away is it?
downward range or how far away?
No, range is only your horizontal.
Oh, okay.
Range is, when you're talking about range, you're only talking about the horizontal distance, okay?
Okay.
The height would be referring to your vertical distance,
Okay.
okay? And then the rest of those, and then you have 3 questions to work from your book. Do those on another sheet of paper. Do not try and work them here, okay? Do not try and work them here. Okay, I'm done. You're on your own.